last time we talked about this idea of partial differentiation. And so what's partial differentiation? Well, we want to take derivatives of multivariable functions, but it's hard to do. And we say, well, we got these great single variable calculus tools. Let's use them. And so partial differentiation is the idea of let's just take a slice and look at a part of the function. Maybe where I'm holding x fixed or where I'm holding y fixed, and then I go back and use my old tools. Well, that works pretty well in the slices, and it turns out to work pretty well in general. In fact, there's really no new tools that we're going to learn. It's taking our old single variable tools and applying them to this multivariable setting. And so it's going to be fun. Now, one of the things that often we talk about is this notion of differentiability. And we say, well, what does it mean to be differentiable? So in single variable calculus, we said, well, it's differentiable means I can take a derivative. But there's another way to think about it, and that's important as we think about, okay, how do we generalize? When we say we can take a derivative, the idea of what is the derivative? Well, it says when I zoom in really close, what I'm looking at looks very flat. And the flat thing is a line, and that derivative is the slope of that line. So another way to think about the notion of differentiability is that I'm locally flat. Okay, well, what does that mean? Well, to say that you're locally flat in 2 dimensions, what that says is if I have a curve, and if I zoom in, what do I see? Is I see a nice flat thing. Well, what happens if I'm in 3 dimensions? Well, I don't have a curve. When I look at the function, what I end up seeing is some sort of a graph. And if I'm on a point in the graph, if I zoom in, what should I see? Yeah, a plane. It should be something very flat. So that's what we're going to think of. We're going to say, okay, differentiable for us means we want to be flat. We want to be something flat. All right, well, a first guess to say something's differentiable is say, well, we have these partial derivatives. Maybe that's all I need to check. As long as I can take partial derivatives, it seems reasonable to say I'm a flat thing. And the answer is, it's more subtle. It's more subtle. It's kind of similar to like limits. Limits can be subtle. So let's do a quick example here where we can have partial derivatives which are 0. In other words, they exist, but our function has problems. So here we go. I'm going to look at the function the square root of the absolute value of x times the absolute value of y. And I want to talk about these partial derivatives at the origin, at 0, 0. Now, when I'm looking at a partial derivative, how do you go about computing a partial derivative? I mean, what's the actual mechanics? Do you recall? Hold one variable constant and look in terms of the other. Okay, so when I'm asking for a partial derivative, so say I want to take the partial derivative with respect to x. So I'm looking here in my xy plane. This is my domain. And I want to say what's happening when I'm holding y to be 0. So I'm looking just along the x-axis and saying, what's my function behaving like? Well, what is my function behaving like? So if I look at f of x comma 0, what do I get when I plug in x comma 0? You get 0. What's the derivative of 0? 0. Okay, good. You know that one. Okay. So that tells me that when I look in that slice and I look at the origin, the partial derivative of f with respect to x is 0, which is not surprising because it's flat. Well, all right. What if I want to do the partial derivative with respect to y? Well, in that case, I fix my x. I'm saying, well, what happens along this segment? So in other words, f of 0 comma y. Well, what is f of 0 comma y? It's still 0. And so the partial f partial y is still 0. Okay, so the partial derivatives are 0. I claim, though, this doesn't look flat. Now, I'll show a picture, which might be convincing if you think the picture is accurate. But even if we don't have a picture, we can still say, what if I look along this direction, along the line y equals x? What does my function look like? So if I look at f of x, so that's along the line y equals x, I'll have the square root of x times x. And the square root of x times x becomes absolute value of x. So in other words, when I look along the diagonal, it looks like a v. That's definitely not flat. No matter how close I look, it's always going to look like a v. All right, so what does it actually look like? Well, it looks something like this. And what you can see, it's kind of hard to make out a few things, but you can see there's this flat part. This is along the y-axis. There's another flat part running along here. That's the x-axis. It's a little bit obfuscated, but over here, that's the origin. It's sort of like the Sydney Opera House of functions. But you can see there's like a pinching that went along here. And if you zoom in, it's not going to become flat. Okay. So it's not enough for the partial derivatives to exist. But the good news is it's almost enough. So what do you need? Well, you just need to say, not only do you have the partial derivatives, but in fact, there's reasonable functions. By reasonable, we use the word continuous, which means, in other words, they're the kind of functions that you'll see. So as long as our functions look nice, then in fact, as long as we can take our partial derivatives, we do have things which are differentiable. So now we have to say, well, why is that? Well, okay, so let's think about it. So here's the idea. I'm going to look at f of xy minus f of ab. And what I really would like to be true is to say that f of xy looks like a flat thing. So I want to make f of xy look like a plane. That's my goal. Nearby the point AB, I want it to be flat. So we're going to do a very popular trick in math, which is I'm going to add and subtract something. So I'm going to add and subtract this f of x comma b. Now if I add and subtract the same thing, I haven't changed the function. It's still the same function. But what I have done is said, well, perhaps if I look at it now in two different pieces, each piece I can understand. So what's the advantage of doing this? If I come to the original expression, notice how it differs in the first coordinate and it differs in the second coordinate. So x versus a, y versus b. If I come to here, you'll see now they actually match. X and x in the first coordinate, they differ in the second coordinate, while over here, they differ in the first coordinate, but they match in the second coordinate. Now why is that special? Well, when I agree in a coordinate, what that means is I'm in a slice. If I'm in a slice, I can now go back and think about what's happening in single variable calculus. So you might remember that in single variable calculus, we had this basic rule of thumb. We said, if I look at g of x minus g of a, it's approximately g prime of a times x minus a. That was our old single variable calculus idea. This is just another way of saying that the function is about the tangent line. Well, we want to do the same thing. And now we say, okay, we're going to work in the slices. So we get the following. In the second term, they disagree in the first slice. So here I'm going to think about, I'm looking at the slice y equals b. And I'm going to say, okay, so if I'm in y equals b, I'm holding my y coordinate fixed. Now I'm looking at a perturbation in just the x direction. So I'm asking for a partial derivative with respect to x. And I can say, well, this is approximately f sub x at ab times x minus a. So it's acting like the g prime of a times x minus a. this f sub x of ab plays the same role as this derivative. Because it is. It's the derivative in the slice. Now we just switch coordinate names. The same thing happens over here. But now we're in the x equals x slice. Well, not the greatest name. And it's the y that's varying. And so we get the f sub y of x comma b, y minus b. So far we're okay. But how do we finish up? Well, we made it an assumption. We want the partial derivatives to be continuous, which means that they don't change very much. So here's the last little change. I'm going to, instead of evaluating the partial derivative at the point x comma b, I'm going to evaluate it at a comma b. And I'm okay to say it's about the same. And this idea of approximation comes from the idea of my function's continuous. So now we put it all together, and lo and behold, we get the following. We can say that our function, f of xy, is approximately the value of the function at ab plus f sub x evaluated at ab times x minus a plus f sub y at ab times y minus b. And the important thing here is to say, hey, this right-hand side, that's a plane. Now, it may not obviously be a plane right away, but if you look at it, you could say, well, suppose I set this whole expression equal to z, you'd see you have all the right ingredients. Something times z, something times x, something times y, and a bunch of constants. So this is a plane. And not surprisingly, we call it the tangent plane. So the tangent plane to f of xy at the point AB. It's also called the linear approximation. So like tangent lines are approximations to functions in single variable, tangent planes are approximations to functions in multivariables. Now, you're strongly encouraged to learn this formula. As demonstration, I will now put a box. The most ringing endorsement you can get in calculus is to box something. And so you should be familiar with this. All right. So let's take a look at what this looks like. So you might remember this picture from last time when we looked at this surface and we said, well, we'll look at various slices when we're taking our partial derivatives. So it's the same picture, nothing's changed, but just I want to sort of say, okay, does this make sense? So I have my tangent plane, f of ab, f sub x at ab times x minus a, f sub y at ab times y minus b. And so I have a point. So you should think of this point down here. This is the point a comma b. And the f of ab, that's my height. So f of ab is how far up I go. Now what's happening to these partial derivatives? Well, think about the slices. So if I look here, say, let's for a second hold y fixed. So I'm on this green part right here. So if I look in this part downstairs, what do I see? Well, what I see, I'll move this up a little bit here, is I see a nice curve. Now, where is this curve at? It's at, if I'm in this green part, this is at x equals a. That point drops down to x equals a. And if I look at my tangent plane, when I'm at y equals b, because I'm in the y equals b slice, that term vanishes, and lo and behold, what do I have? The value of the function f of ab, which is the height, plus the derivative times x minus a. In other words, when I slice the plane, I'll get the line, the tangent line. So the tangent line comes from the tangent plane, and vice versa. Similarly, if I slice where I hold x fixed, okay, so if I hold x fixed, x equals a, I see this piece of the curve down in the yz plane. And the point, if I drop straight down, well, that's at y equals b. I get the same height as before, f of AB, and this line comes from the tangent plane, where this part now zeroes out because I have x equals a. So these two lines come in from the two different slices. So we can add them into our picture. They look something along the lines of the following. And lo and behold, what do we get? Well, we're really just seeing the pieces of the plane. Now, one of the ways you can think about this is you can sort of say, well, there's three parts. The value of the function, the f sub x, the f sub y. So the value of the function is more or less moving it up and down. What do the f sub x and f sub y do? Well, they're acting like tilts. So you can tilt in one direction, or you can tilt in a different direction. And that's what they're doing. So if there's actually a game, a marble game, and nowadays most people play it on their phones, where you would tilt and the marble would roll. And the idea is, by modifying these partial derivatives, you can actually change how the plane sits. So that's what the f sub x and f sub y are doing. All right. Good. Now, for something a little different. Any questions about tangent planes? We will have practice in finding these over the next few days. And I strongly encourage you to anticipate that you should know how to find tangent planes, because they're a very important thing. They're the flat thing. In calculus, we like flat things. All right. Next thing, the chain rule. So our goal is to get a chain rule for multivariable functions. All right. Well, why? Well, the chain rule is a very fundamental thing. It's probably the most important rule for single variable calculus. And because the chain rule is how you put functions together, one inside another. And most of the times when you're building functions up, a lot of it comes down to expressing it in terms as one function inside of another function. All right, so we want to build up the chain rule. Okay, well, what do we have? The way I like to think about things is I like to think about what are the variables involved and how are they related. So we're going to start in a special case and work up to things that are more complicated. So our special case to start with is where I'm going to think of my z variable is a function of x and y. And then my x and my y are both functions of t. So if you think about what this means, you can think of it as I have a particle moving. X and y are determining its location in the xy plane at a given time t. And then my z is, say, what's the height of that particle at that time. All right. So z depends on x and y. X and y both depend on t. Now there's a comment here which says z is a function of t. In other words, if I know t, I know z. In fact, I can really think of z as being a single variable function. It's totally dependent just on t. And the question becomes, how? How does z change with t? All right. So the way we're going to do this is we're going to start with the linear approximation. Now, where does the linear approximation come from? It's just another name for the tangent plane. So I've changed notation slightly, but other than that, it's the tangent plane. So what do I mean by changed notation? Partial f partial x is the same as f sub x. And I moved my f of ab back across. My z is f of xy. All right, so f of xy minus f of ab, partial f partial x at ab times x minus a, partial f partial y at ab times y minus b. Well, we want to sort of think of these pieces and say, well, what are these? And some of them are pretty straightforward. In fact, I think all of them are more or less straightforward. And I say, okay, let's go through it. F of x, y minus f of ab, what am I trying to look at? Well, I'm trying to say it's a difference. When you see a subtraction, how is something changed? And what has changed? Well, it's the z, because z is f of xy. So this is the change in z. Ever see a capital delta, think it means for change. Partial f partial x is just a way of saying, how does z change with x? So partial z partial x minus a is my change in x. Partial f partial y, I can call partial z partial y. And y minus b is delta y. All right. So putting this all together, we divide everything by delta t. So we get change in z over change in t is equal to approximately partial z partial x, change in x over change in t, partial z partial y, change in y over change in t. All right. Well, what's our last thing? What do we want to do? Well, we want our approximation to get better. How do you get your approximation to get better? Yeah, you make your delta smaller. So your approximation gets better the closer you're at. So I want to make this delta t very small. How small should I make it? Very small. So I'm going to let delta t keep getting smaller and smaller. Someone suggested infinitely small. Well, okay, so the idea of infinitely small is the idea of limits. So you're going to let delta t go to 0, and lo and behold, you're going to get something, another box. Wow. So as delta t goes to 0, and I don't know why that says son. It shouldn't say that. It should just say so. All right, we'll fix that in post-production. So what happens is that the approximation is going to become an inequality because our error gets smaller the closer we are. And so what would we get? Well, the change in z over the change in t becomes dz dt. And that's going to be partial z partial x dx dt, because again, change in x over change in t, as I let delta t go to 0, becomes dx dt, partial z over partial y, and then similarly dy dt. So let's go back to the diagram. What am I after? Well, I'm after how does z, which is the part at the top, change as I change t. Now t shows up in two different places. So essentially t has two effects on z, and we have to keep track of both. So t will affect x, and x will affect z. So how do I find the net effect? Well, you can mark on the diagram the following. If I want to know how z is changing with x, that's a derivative. So I'm going to write partial z partial x. I'm using the partial symbol because, whoops, I should say z. There we go. Because z is a function of more than one variable. And then if I want to know how does x change with t, well, that's dx dt. So if I want to now know the net effect, well, to know the net effect is I multiply these together. Partial z partial x times dx dt. So that's how much t is affecting z through the variable x. But of course, I have another variable. So I can go through the other direction. Partial z partial y, that's how z changes with y. And then I have also dy dt, how y changes with t. And so, again, the net effect, multiply them together. So once you have the diagram, the rule is, look, just start with the variable at the top, work your way down, and multiply it. Add up all the pieces, and you're done. That's it. One side note, why do we use the d here, the dz over dt?
Because two partials make a whole.
Two partials make a whole? Wow. That's, well, no. Single variable. That's the key. The d in the partial notation, the only difference is how many variables are involved. So when we write dz dt, we're saying we recognize z as a function of just a single variable t. And so we're going to put it in as a single d instead of the partial. All right. Time for an example. So we have the following. Sand is pouring out, forming a cone. At a particular moment, the radius of sand flowing is 10 pi cubic feet per minute. The radius is 3 feet, and the radius is changing at 1 feet per minute, and the height is changing 2 feet per minute. What is the volume of sand at that moment? All right. Well, what are we looking for?
Volume of sand.
Yeah, we're looking for volume of sand. And we know we're looking for volume of sand because we're told, what is the volume of sand? Okay, so I'm looking for a volume. So it's probably a good idea to know the volume. Now, in this case, what do we have? Well, the sand is coming out, and it's forming some shape, which looks like a cone. So it's forming a shape like that. I don't know where the sand is coming from. It could be like an hourglass, where you have sand dropping from the top half of the hourglass to the bottom half. It could be there's a conveyor belt where it's dropping sand. It doesn't matter for the problem. But we're forming this shape. Now, when you're trying to find the volume of a cone, there's two important things. There's the height of the cone, and then there's the radius of the cone. And it's not given to us, but we do know the volume for a cone. Does anybody know it off the top of their head? Oh, you guys are good. 1/3 pi r squared h. Excellent. Excellent. Okay. In case you're wondering, that's probably a formula we would give you, because we're not trying to test you too much on formulas for volumes of cones. Now, I look at that and I say, well, fantastic. I know 1/3 pi, it's just a number. Do I know r? Yeah, I do know r. How do I know r? It's given to us. Sweet. So we're practically done. R is 3. What don't we know? We don't know h. Okay, so now we have the problem. How do you find h? So our new problem is, let's find h. So r equals 3. H, we don't know that, but we'll find it, I'm sure. H is to be determined. What else do we know? So, because we have all these various numbers here. So the rate of sand flowing is 10 pi cubic feet per minute. What is that? dV dt. How is our volume changing? So we have a dV dt. So dV dt is equal to 10 pi. What else do we know? dr dt. The radius is changing 1 feet per minute. How does that translate? dr dt is 1. And finally, this last statement, the height is changing 2 feet per minute. What is that? dh dt, which is 2. Okay, all right. So we don't know r, but we do know lots of rates. So how do we get this all together? Well, what we have is we have the following. We have volume is dependent on r and h. Because we can see it in the formula right there. There's an r and there's an h. So volume depends on r and h and r both depend on t. So what can we say? If only there was something that we recently talked about that could apply to this setting. If we could just somehow chain our thoughts together, we might find something relevant.
Write v as a function of t.
Well, how could I write v as a function of t? Because I don't know what r and h are as functions of t. But even if I don't know what r and h are as functions of t, what can I do? I can take the derivatives with respect to t. So I can say the following. I can say that dv dt is partial v partial r times what? dr dt. So the partial v partial r dr dt plus, what comes next? Partial v partial h, derivative of v with respect to h times dh dt. So I can talk about how does the volume change with respect to time, and the answer is, well, it changes through a combination of things. So this is the partial v partial r, here's the dr dt, here's partial v partial h, and here's dh dt. Well, let's plug in what we know and see, hopefully, that maybe we get something. All right, do we know what dv dt is? Yes, 10 pi. Okay, do we know partial v partial r? Well, we can certainly take the partial derivative, so let's come up to our formula. What is partial v partial r? Two-thirds pi r h. Because we're taking the derivative with respect to r, treat h like a constant. So I have 1/3 pi h, and then the derivative of r squared would be 2r. Okay, what about dr dt? What is that? 1. Okay. How about partial v partial h? 1/3 pi r squared. And then dh dt, which is 2. All right. Now, some good news. Everything has a pi, so that goes away. Cancel off all the pi's. And we also know r, so we can plug in r equals 3. So if we do that, we get 10 is equal to 2/3 times 3 times h. So that's 2h plus 1/3 times 3 squared. So that's 3 plus 6. So 10 is 2 times h plus 6. So that is something we can solve for h. 2h would be 10 minus 6, which is 4. So h would be 2. Aha! H is 2. Okay. Well, so now we know r and h. So are we done? Almost. Remember, what were we looking for? A volume. So our answer better be a volume. So remember to answer the question that was asked. Okay, so we plug in r equals 3, h equals 2, 1/3 times pi times 9 times 2 for a grand total of 6 pi. And if I wanted units, what would the units be? Feet cubed. 6 pi feet cubed. Good. Okay, so now let's do another one. This one's a little bit more abstract. Suppose that we're given z is x times y. Whoop, let me bring that down a little bit. X is f of t, and y is g of t. Use the chain rule to find dz dt. So we really are back into the same we were talking about a moment ago, where I have z depends on x and y, and then x and y both depend on t. So I can write down the formula. So we have that dz dt is equal to partial z partial x dx dt plus partial z partial y dy dt. Now we're going to go through and fill these out. Partial z partial x, what is that? So again, z is x times y. If I take the derivative of x times y with respect to x, what do I get? What? Well, I'm asking the question because, no. Okay, yeah. Partial z partial x is indeed y. All right. And then how about dx dt? Well, x is f of t, so dx dt would be f prime of t. plus, okay, partial z, partial y. So take the derivative of x times y with respect to y. What do you get?
X.
You get x times dy dt. Well, what is dy dt? G prime. Now, in some sense, we're done. But let's rewrite this one more time. Okay, so we're taking the derivative of z. So z is x times y. Well, that's f of t, g of t. That's equal to y. Well, what is y? Y is g of t. So I'm going to write this, I'm going to just change the order just to make it look prettier. F prime of t times g of t plus x. What's x? F of t. And then times g prime of t. Well, what's that? Other than the fact that I've lost it on the edge. What do you see? It's the product rule. See, isn't this cool? Now you say, I don't have to memorize the product rule anymore. I'll just use the multivariable chain rule and it pops right out. One less thing to remember. Ah, fantastic. Fantastic. Okay. All right. A few more examples to get us going. So, the moral is we can do things which are more complicated. The idea is just work through the diagram. So, what do I mean by more complicated? Here I have z, which depends on x and y. Because it says z is a function of x and y. And now, x depends on two variables, s and t. And y, similarly, depends on two variables, s and t. And it says find partial z, partial s, and partial z, partial t. Why am I using the partial notation and not the d notation? It's multivariables. What does z really depend on now? S and t. So it's whatever's at the bottom. That's what it depends on. All right, so if you learn to read the diagram, it's actually not too bad. So if I want to find partial z, partial s, what I do is I ask, okay, where are my s terms at? There's two of them. And I look at how I can get to the s terms. So for every s term I have, I'm going to have a piece being added up. So in this case, I'm going to have two terms. One that comes for that s, one that comes from that s. And what are my two terms? Well, here I'm going to go first, how does z change with x? Partial z, partial x. And then I'm going to ask, how does x change with s? Partial x, partial s. So I'm working my way down. What would my second term be? Partial z, partial y. How does z change with y? And then partial y, partial s. All right. Now, what if I wanted to do with respect to t? Partial z, partial t. Well, here I see, aha, I have two times that t shows up. And so for every time t shows up, I look at all the ways I can get down. So what do I have? Partial z, partial t, the way z changes with t is partial z, partial x times partial x, partial t plus partial z, partial y, partial y, partial t. All right. Okay, one more, and then we'll go to our final topic after that. Suppose you have z is f of x and y and t. So you can, and then I have x and y are also functions of t. So let's be a little bit careful here. So I have, I'll write f now, just to be, so I don't confuse. F depends on x and y and t, but x depends on t and y depends on t. I can think of it as I have this surface which is changing with time. So that's my f of x, y, t. So I have the surface which changes as time changes, and in the meantime, I'm moving around. That's my x of t, y of t. And so I have lots of things moving all at the same time. I should turn this a little bit, make it more, there we go. So if I want to know how is z changing with t, well, I say, how many t's are there? And the answer is that there's 3 of them. So if I want to find dz dt, how many terms will I end up with? I'll end up with 3. So what are they? Well, you look at how you get down to the t's. So you're going to go f down through, start with f to x, which I'll denote that as f sub x, and then go to x down to t. So dx dt. Plus, now you go through the next route, f sub y. How does the function y change with respect to y? And then you have dy dt. And finally, you go look at f sub t. Now you might say, is it okay to have these variables at different heights in your chain? And the answer is, yes, it's absolutely okay. You are allowed to do that. All right. Any questions? Yes.
For the first question, I'm assuming I can, but I just want to cancel out the partial x with partial x top and bottom.
Sure, of course. There's a strong tendency. You look at this kind of expression, you say, oh, look, the partial x's cancel, the partial y's cancel. But here's the thing you have to be careful of. When we write partial z over partial x, it doesn't mean like there's this thing called partial z, and there's this other thing called partial x. So they're not like linked together, the two things put together. It's just a notational thing that makes it look like it's a fraction. So partial z, partial x is not really one thing divided by another, but it's just a way of saying, I'm going to write this expression, and I'll put it into a fractional form, because I'm thinking about what it represents. But no, it's not like these partial x's get to cancel. Now, intuitively, it's like, hey, it's kind of like they cancel, right? Wink, wink, nudge, nudge, because it kind of makes sense, but they don't actually cancel. All right. So it's time for us to get a little implicit, or maybe a little bit explicit. And so we're going to talk about explicit and implicit functions. Now, what is that? Well, explicit and implicit functions are really just another way of saying, how clearly defined is your function? So when I say I have an explicitly defined function, that says I can rewrite my function in terms of z equals stuff with x and y. Now the variable names aren't important, but the important thing is I can solve for my variable that I'm interested in. So that's an explicit relationship. In implicit relationship, I can't do that. There's no way for me to isolate a variable, or at least not to isolate the variable I want. So for instance, here I have e to the z plus sine of xz. I have 2 occurrences of the z. I could get my z out of the e to the z, but only at the cost of getting that sine of xz. That z would be even more buried. And vice versa, I can get this z out, but that would bury the other z even further in. There's just no way to solve for z. Now, okay, you can't solve for z in a nice way. Does that mean that, you can't say anything? Well, no. So an implicit relationship says, look, there is a relationship. If you tell me something about x and y, it does give me information about z. So there's a dependence. All right. Well, if I know that z depends on x and y, even if I can't get the function, I want to know, can I at least say something about how z changes with x, or how z changes with y? And the answer is yes. And how do we do it? Well, we said we cannot solve for z as a function of x and y, but here's what we do. We think we can. So we think we can. And we say, let z be a function of x and y. And you might say, but which function? No, 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 no. Don't think of it like we're going to solve for it. Just treat it like it were. And now that you can say, aha, I have this function z of x and y, now you can start to get to work. Okay, what do I mean? Well, suppose I have f of x, y, z equals 0. That's a little bit hard to read there. And I want to ask, okay, how does z change with x and y? Well, f of x, y, z equals 0. It's like I took this expression, I moved everything to the other side, so I set it equal to 0. It's not really important that it's 0, but all right. That says that there's a relationship. I'm going to think of z as being a function of x and y. So I can say, aha, the function as written depends on x, y, and z, but now z will depend on x and y. So here are all my variables put together. And, oh my gosh, I'm off the screen. There we go. That's a little better. Okay, well, what happens next? We take the derivative of everything. Let's take the derivative with respect to x. When I take the derivative with respect to x, how many terms will I get? I'll get 2, because x shows up twice. It shows up when I take the derivative of f with respect to x, but it also shows up derivative of f with respect to z, derivative of z with respect to x, and so what I get is on the left-hand side what I just talked about: derivative of f with respect to x, derivative of derivative of f with respect to z times partial z partial x. That's the derivative of the left-hand side. Derivative of the right-hand side. What's the derivative of 0 with respect to x? It's 0, because it's not changing. If it doesn't change, your derivative is 0. All right, so you get f sub x plus fz partial x is 0. Well, rearranging, I can now say that the way that z changes with respect to x is minus fx over fz. Okay, well, that's if I took the derivative with respect to x. What else could I do? I could take the derivative with respect to y. Same process. So we do the same thing, but this time we do it with respect to y. And if we do that, we get f sub y plus f sub z partial y is equal to 0. So the derivative of z with respect to y, or partial z partial y, is negative f sub y over f sub z. Now how does this work? The rule here at the bottom. Always remember to treat z as a function of x and y, and then take derivatives. So let's do some examples using implicit differentiation. So here we go. Find partial z, partial x, and partial z partial y, given z plus e to the xz plus sine of xy plus y cubed equals 17. Now this is implicit because here we can't solve for z. There's no way to do it, because I can get this z by itself, but there's an e to the xz upstairs. So there's no way to solve for z. But the key to this problem, and the key to every implicit differentiation problem, is I'm going to think of the following. I'm going to say, really, every time I think of z, I'm always going to say that it's actually a function of x and y. Now, I don't know which function it is, but I'm going to think of it that way. So that when I'm looking at this equation, I say, aha, it's really z, which is a function of x and y, plus e to the x times z, which is a function of x and y, plus sine of xy plus y cubed equals 17. Now, I usually don't write this out, but mentally, this is what we think of. And now we say, okay, what do we want? Well, we want to take the derivative with respect to x. So that's the downstairs part. So this says derivative of z with respect to x. All right, so here we go. Let's actually switch colors, make this more colorful problem. So derivative with respect to x. So I'm going to go through, and everywhere I see an x, I'm going to take a derivative. So reading along, I see a z. Well, it doesn't say x, but remember, it's really z of xy. So there is an x hidden. So I say, okay, what's the derivative of z? Well, it's the derivative of z with respect to x is the derivative of z with respect to x. Go to the next term, e to the xz. And notice, again, z is a function of x and y, so there's actually two things multiplying together that involve an x. So we're going to do the chain rule, e to the xz, times the derivative of x times z. All right. So again, remember, product rule here. So derivative of x is 1 times z, which is z, plus x times the derivative of z with respect to x, which is partial z partial x. Plus, now we go to the next one, sine. Well, derivative of sine, cosine of xy. Take the derivative of the inside with respect to x, and we're left with y. You might say, whoa, wait a second. When we were taking derivative with respect to x of z, we got partial z partial x. Why don't we need to do a partial y partial x? The answer is, in this setting, we're thinking of z as dependent on x and y. So x and y are the variables, which means they can vary independently. They don't rely on each other. So there's no relationship between y and x. It's a relationship between z and x and y. All right, derivative of y cubed, 0, because I'm taking derivative with respect to x. Remember, derivative with respect to x. Okay, that's derivative with respect to x. At the left-hand side, derivatives have to match. So take the derivative with respect to x on the right-hand side, we get 0. Now, after you take the derivative, you gather. So, we gather what? Well, we look at all the terms that have a partial z partial x. So that's a partial z partial x. And there's one of those plus x e to the xz. Okay, and then everything else. So what's there? Well, z e to the xz and cosine xy times y. I'll put the y in front so it looks nicer. Y cosine xy equals 0. And at this stage, all right, move that over, and then we're going to divide. So doing that, we get the following. Derivative of z with respect to x is negative of z e to the xz plus y cosine xy all over 1 plus x e to the xz. Done. Done. Good. Now, that's one part. Remember, we want to find two derivatives, so now let's do the other part. So, derivative of z with respect to y. The downstairs says we're taking derivative with respect to. So, partial y. Derivative with respect to y. Do the same process. Go to z. Well, even though there's no y written, we remember it's z of xy. So derivative of z with respect to y is derivative of z with respect to y. Plus, next term, e to the xz. Well, there is a y. It's inside the z. That's the only y. So what's that going to be? Well, it's e to the xz times the derivative of xz. Well, x is acting as a constant, so it's going to still be there. Then partial z, partial y. Now, next term, derivative of sine of xy with respect to y. Well, that'll be cosine of xy times the derivative of x times y with respect to y, which will be x. Last term, derivative of y cubed with respect to y, that's easy, 3y squared. That equals 0. So now, in fact, it's a little easier to see what happens because the first two terms, they have partial z partial y. Factor that out. 1 plus x e to the xz. You might notice, hey, they match. Coincidence? No, it's not a coincidence. They came from the same place. These terms came from when we took a derivative of z with respect to something. So they should match. And then, of course, you have the rest of it. Well, that doesn't match. And that's okay, because that's when you took derivative of everything else. And it's not the same function when we have x swapped with y. So we do this, what we did before, move it over, divide, and so we can conclude derivative of z with respect to y is negative of, and here we'll have cosine of xy times x plus 3y squared divided by 1 plus xe to the xz. Done. All right, good. Well, one more example. Last example. And this one is a little bit of a challenge one. Suppose we're told that f of x, y, z is 0. So again, this is our implicit relationship. So what we have is we have that f depends on x, y, and z. And because of this relationship, f of x, y, z equals 0, we say, aha, z also depends on x and y. Well, now that I know that z depends on x and y, I can ask the question, how is z changing with respect to y? Well, but we're going to go even further. The second order derivative. Second order derivative of z with respect to x and y. So it means I have to take two derivatives. So we're going to find this in terms of the derivatives of f. All right. Well, this should be fun. Well, if I want a second order derivative, the first thing is start by taking first order derivative. So let's start with respect to y. No problem. So it doesn't really matter which one because there's this nice symmetry that goes on. All right, so what am I doing? I'm taking the derivative of both sides with respect to y. Well, the 0 part is easy, so I'll actually do that one first. Derivative of 0 with respect to y is 0. Now I come to f of x, y, z. And that's told that that's equal to 0. Well, so if I'm taking the derivative with respect to y, I come over to my diagram, and I say, well, y shows up twice. So if I'm going to take the derivative with respect to y, I'm going to end up with two terms. So I'm going to have, first off, f sub y, which is this part right here. And then I'm going to add to that f sub z, which takes us to here. And then the derivative of z with respect to y, which is partial z, partial y. Now recall that we said, aha, that tells us that the derivative of z with respect to y is equal to minus f sub y over f sub z. But we may or may not need this. It also might be useful to recall, similarly, which is a hard word to say, that partial z partial x is minus f sub x over f sub z. But we'll get back to that. Okay, so I took one derivative, and that first time I took it, I took the derivative with respect to y. So now we're in round 2. We're taking our next derivative. So we're going to switch to our new color. Since I took the derivative with respect to y, the next thing is, let's take the derivative with respect to x. Well, the derivative of 0 is still 0. 0 equals. Now I come to f sub y. Well, I know how f depends on variables. How does f sub y depend on things? And the answer is that f sub y has the same tree. So in other words, it looks identical. It still depends on x, y, and z in some way, and z still depends on x and y. So if I'm taking the derivative of f sub y with respect to x, well, it says start with f sub y, take derivative with respect to x. So f, y, x. But you're also going to need the following, namely f, y, z, so f sub y, derivative with respect to z, times partial z partial x. Okay. So this comes from the f sub y. Plus, now I come to here, product rule. Okay, well what's the tree for fz? The answer is the same as the rest. x, y, z, x, y. So, taking derivative with respect to x, I'm going to have fzx down here, then plus fzz, which is there, partial z partial x. And now this is all multiplied by partial z partial y. So derivative of the first times the second plus fz, and now I'm going to have the derivative of partial z partial y with respect to x, which is partial squared z partial x partial y. And now it's good to sort of celebrate. In some sense, we're like, hey, that's what we're after. We were after that second derivative. Now what we have to do is figure out what to do with everything else. Well, what can we do with everything else? Well, let's start and see what happens. So you have 0 is fyx plus fyz. And these terms are okay because they're derivatives of z. But now partial z partial x. Well, here's where we go back to what we know. This is minus fx over fz. Okay, plus fzx plus fzz. Then I have a partial z partial x. Again, minus fx over fz. Partial z partial y? Well, minus fy over fz plus fz, and then I get partial squared z partial x partial y. Well, good. Everything's now in terms of derivatives of f. We want to just clean it up, polish it, make it look beautiful. One thing is, I see fractions. I don't like fractions. I want to get rid of fractions. Fractions and me, we don't get along too well. So I see, okay, if I multiply by fz squared, that will be enough to get rid of all my fractions. So here we go. Everything is going to get multiplied by fz squared. And at the same time, I'm going to distribute. So I'm going to get 0 equals fyx fz squared. Now here, I'm going to cancel one fz, so I'm going to get minus fyz fx fz. Now the next term, well, it'll be distributing, so it's still minus fzx fy fz. So that's that term. Next term, well, is going to be minus minus makes plus fzz fx fy. And then finally, plus fz cubed, partial squared z, partial x, partial y. And now, maybe we can make it fit on the last bit of space down here. What's left? Well, we're going to move all of that to the other side. And then divide by that fz cubed. So we get partial squared z partial x partial y is equal to, and we're just going to read off, remember we subtracted over, minus fyx fz squared plus fyz fx fz plus fzx fy fz minus fzz fx fy, all divided by fz cubed. Exactly as you would have thought. Well, actually, probably not. I mean, it's not so obvious. And it's a hard thing to derive. But there's a process. And the point is, it's the same process that we had, which is be careful, be methodical. Make sure you remember how the variables relate to one another and work it through. And then you too can solve fun problems. All right. Well, that's it. Back to our regularly scheduled class.